I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is from the section Linear Algebra and is related to the nilpotent operators. This question is placed in the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704073. Right. The given question is, let V be a finite dimensional real vector space and T1, T2 be two nilpotent operators on V. Let W1 be the set of all V belongs to capital V such that T1 of V is equal to 0 and W2 is equal to the set of all V belongs to V such that T2 of V is equal to 0. Which of the following statements are false? Which of the following statements are false? We are given four options. Option 1. If T1 and T2 are similar, then W1 and W2 are isomorphic vector spaces. Option 2. If W1 and W2 are isomorphic vector spaces, then T1 and T2 have the same minimal polynomial. Option 3. If W1 is equal to W2 is equal to V, then T1 and T2 are similar. Option 4. If W1 and W2 are isomorphic, then T1 and T2 have the same characteristic polynomial. Let us now discuss the solution of the problem in detail. We are given a finite dimensional vector space V over the real field, over the field of real numbers. Let the dimension of V over R be n. We are given two nilpotent operators T1, T2 on V. That means T1 to the power of K1 is a 0 operator for some positive integer K1 and similarly for T2. Given W1 is equal to the set of all V belongs to V such that T1 V is equal to 0. In a similar fashion, W2 is given as the set of all V belongs to V, T2 of V is equal to 0. This means W1 is the null space of T1 and W2 is the null space of T2. Let's call on the option 1. Let's discuss the validity of the statement given in option 1. Option 1. If T1 and T2 are similar, then W1 and W2 are isomorphic vector spaces. T1 and T2 are similar means what? There exists an invertible operator P such that T2 is equal to P inverse T1P. When they are similar, we recall a property, then their ranks must be equal. This implies rank of T1 is equal to rank of T2. Now we call on rank-nullity theorem. Row of T1 plus nullity of T1 is equal to dimension of V over R. That is, the nullity of T1 is equal to dimension of V n minus the rank of T1. In a similar fashion, we also have the nullity of T2 is equal to n minus rank of T2. Now, nullity of T1 is equal to n minus row of T1 is equal to n minus row of T2, because row of T1 is equal to row of T2, but n minus row of T2 is the nullity of T2. Thus we got nullity of T1 is equal to nullity of T2. That is, the dimension of the null space of T1 is equal to the dimension of null space of T2. That is, the dimension of W1 is equal to dimension of W2. But W1 and W2 are vector spaces over the same field R. Therefore, they must be equal. They must be isomorphic. W1 is isomorphic to W2 since they are subspaces over the same field R. Thus, the option 1 is true. Right. We move on to the next option in the next slide. Option 3. If W1 is equal to W2 is equal to V, the whole vector space, then T1 and T2 are similar. Now W1 is equal to V means what? Means T1 of V is equal to 0 for all V belongs to V, because W1 is equal to V. So that means T1 is sending every element of the vector space V into the 0. Means what? T1 is a 0 operator. Similarly, W2 is equal to V will also imply T2 is equal to 0, that is the 0 operator. That means this means W1 is equal to W2 is equal to V will imply T1 is equal to T2 is equal to 0. They are equal. So the equal operators are similar. So T1 and T2 are similar because they are equal. Thus, the option 3 is also true. Right. We move on to option 4. If W1 and W2 are isomorphic, then T1 and T2 have the same characteristic polynomial. Agreed. Is it true? That's the question. We have T1 and T2 are two nilpotent operators on V. This means we recall the properties, a property of nilpotent operator. They are nilpotent implies each eigenvalue of T1 is 0, so also each eigenvalue of T2 is 0. When all the eigenvalues of T1 are zeros, then the characteristic polynomial of T1 is x minus 0 to the power of n, that is x power n, and so also the characteristic polynomial of T2 is equal to x power n. Thus, T1 and T2 have the same characteristic polynomial. Thus, the statement given in option 4 is true. Right. We make a remark here. In the option 4, we have proved that they have the same characteristic polynomial without using the fact the given hypothesis W1 and W2 are isomorphic. That is, the given hypothesis W1 and W2 are isomorphic is not required to get the result. Now, we are required to find the false statements. Required to find false statement from the options. Now, out of the 4 options, we have seen that the options 1, 3 and 4 are true. Therefore, option 2 must be false. Therefore, the answer to this question is to find the false statement. The false statement is option 2. Therefore, the answer to this question is option 2. That is the detailed discussion of the solution of the given problem. But our students will ask us that why not we talk about option 2 and show us how it is false. Yes, that we will do in the next slide. Right, the given hypothesis is there, all are there. And option 2, if W1 and W2 are isomorphic vector spaces, then T1 and T2 have the same minimal polynomial. W1 is isomorphic to W2 will imply null space of T1 is isomorphic to null space of T2 will imply the dimension of n of T1 is equal to dimension of the null space of T2 will imply the nullity of T1 is equal to nullity of T2. Now, the nullity of T1 represents the geometric multiplicity of the eigenvalue lambda is equal to 0. And since T1 and T2 are nilpotent operators, they have 0 is the only eigenvalue for those operators. So, nullity of T1 will represent the geometric multiplicity of lambda is equal to 0. This is equal to the number of Jordan blocks for lambda is equal to 0 in the Jordan canonical form of T1. So also, nullity of T2 will represent the geometric multiplicity of lambda is equal to 0 will be equal to number of Jordan blocks corresponding to lambda is equal to 0 in the Jordan canonical form of T2. Right. That means the number of Jordan blocks for lambda is equal to 0 in the JCF of T1 is equal to the number of Jordan blocks for lambda is equal to 0 in the Jordan canonical form of T2. We consider a counter example here. Consider V is equal to R power 4, a finite dimensional vector space over the real field. Let T1 is equal to this matrix 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. It is the JCF of T1 in which we find 2 Jordan blocks. And in T2 also we find 2 Jordan blocks corresponding to lambda is equal to 0. Right? The number of Jordan blocks are same. And this is one Jordan block, this is another Jordan block. Here, this is one Jordan block and this is one Jordan. This is a Jordan block of size 2, size 2, size 2. Jordan block of size 3 and 0. Size 1. Right. Now, you can check the rank of T1 is equal to rank of T2 is equal to 0 because there are only 2 linearly independent rows in each T1 and T2. And we make use of the Rank-Nullity theorem. From that we get nullity of T1 is equal to nullity of T2 is equal to 0. This implies dimension of null space of T1 is equal to dimension of null space of T2. Will imply dimension of W1 is equal to dimension of W2. Will imply W1 is equal to isomorphic to W2 because W1 and W2 are vector spaces over the same field R. So, the required hypothesis is there for these 2 matrices, Jordan canonical forms, W1. So, the W1 and W2 are isomorphic, correct? But the minimal polynomial corresponding to T1 is given by x to the power of s, and the minimal polynomial of t2 corresponding to t2 is given by x to the power of t. What are these exponents s and t? Where s is the size of the largest Jordan block of t1 and t is the size of the largest Jordan block of t2. Right. Minimal polynomial of t1 is x square y. Go to t1. And what is the size of the largest Jordan block in t1? This is one Jordan block, this is one Jordan block. Each is of size 2. Therefore, it is 2. Therefore, it is x square. Minimal polynomial of t2 is equal to x cube, because here we find x to the power of t, where t is the size of the largest Jordan block of t1. We have two Jordan blocks, and one Jordan block is of size 3 and the other is size 1. Therefore, the largest Jordan block, the size is 3. So, it is x cube. So, you have the hypothesis W1 and W2 are isomorphic vector spaces, but these T1 and T2 do not have the same minimal polynomial. One has the minimal polynomial x square, the other has the minimal polynomial x cube. They are not equal. Thus, W1 is isomorphic to W2, but the minimal polynomials of T1 and T2 are not equal. Therefore, the statement that is given in option 2 is not true, is false. Is false. And we have to find out that statement which is false. Therefore, option 2 is false. And our answer to this question is option 2. That is the detailed discussion of the solution of the given problem from the section Linear Algebra, which is related to the concepts of linear operators. In my opinion, this problem is not that easy. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.